Okay, so by now you should have recognized that I'm not going to be here for the next 3 days, but we are not going to entirely waste that time. So we will learn a few new things. However, on the bright side, you will not be having any homework. So if you have not done the catalyst, pause this video and take 3 minutes to do the catalyst. But hopefully you have, and so I'm going to go through it right now. These conversions are exactly the same as the conversions we did with grams to moles. You underline what you are given and what you're trying to find, and then we're going to write it out like this. So this will be 89.2 torr times, and then what I'm trying to find here is ATM. And torr goes on the bottom, ATM on top. And so these numbers come from to your left right now on those cabinets, that pressure conversion sheet. So obviously it's 1 ATM, you can see up at the top. But for torr, you're going to have to go down a little bit to 760. And if you do this math, it should be 1.183 ATM with 4 significant figures. For this one, the conversion is very much the same. It's just that it's PSI, and so the equivalent statement there would have been 1 ATM is equal to 14.69 PSI, and that one's a little bit further down, but the answer here should be 5.33 ATM. You would have done the exact same thing as up here. And then the last one, it also would be the same setup. This is your given, this is your unknown. What you had to know here was that 1 liter is equal to 1,000 milliliters. And so you would have done the exact same setup here. And so this answer would be 0.5469 liters. That should be L there. So that's our catalyst, and these conversions are going to be very important today. So if you're having trouble with those, ask a classmate, the person sitting next to you, when you get started on some of these practice problems. That's probably somewhere that you're going to need some help. So I'm going to scroll us down here a little bit, give us some new space to work with. Okay, so today the objective, let me get a color here, maybe blue. The objective is to use the ideal gas law to calculate the pressure, the volume, the number of moles, or the temperature of a gas. And so we've seen the pressure, the volume, the number of moles, and the temperature all before. We've been working with those for the past 2 weeks. What we have not seen is this, the ideal gas law. And so that's really where we're going to start this lesson. And even though I'm not in the classroom, we're going to work the same exact way for the notes. So you have questions on your note sheet, and we're going to go through and answer those right now before we get into a practice problem in about 10 minutes. So the first question is, what is an ideal gas? And so the idea here is we want to be able to predict the pressure, the volume, the number of moles, or the temperature. And the best way to do that is when a gas is at ideal conditions. And so this definition is actually pretty simple. An ideal gas is a gas at STP. And so STP, you'll remember from last week, was standard temperature and pressure. And so when a gas is at this standard temperature and pressure, so standard, ideal, they're kind of going with the same idea here, that the gas, we can predict how the gas particles will behave. And so using that information, we can predict the volume, the pressure, the number of moles, or the temperature. So that's what the ideal gas is. And just to make sure we're all on the same page, STP, that's standard temperature pressure. That's kind of like the go-to standard temperature and pressure. So the standard temperature is 273 Kelvin, and the standard pressure is 1 atm. So if I say that something is at STP, then you know that the temperature is 273 Kelvin and the pressure is 1 atm. So right now, I'm going to give you 2 minutes. So let me write that over here. Actually, no, you know what? Let's give you 1 minute. 1 minute to answer that quick write that is on your page. So what you're doing is pretty much summing up these 2 points. What is an ideal gas, and at what conditions does that exist? So 1 minute, write silently. I'll stop you in 1 minute and we'll move on. Okay, so we're gonna keep moving here down to our next point. And so the next point, so I'm going to scroll down just a little bit here, is what is the ideal gas law? So now that we know what an ideal gas is, which by the way, for a gas to be considered an ideal gas, it doesn't have to be exactly at STP. We're just kind of assuming that gases that are near it, generally near it, will behave the same way. And so here is the actual equation. It's PV equals nRT. And so you already have that written down. So the next question is really, when would you use it, or why would you use it? And so I'm actually going to give you kind of a non-example first. So first we're going to talk about the equation we've been using, which is P1 V1 over T1 equals P2 V2 over T2. So I'm going to give you 30 seconds to look at this equation right here, PV equals nRT, and compare it to this equation here, P1 V1 over T1 equals P2 V2 over T2. And I'm going to give you 1 minute to look, compare what is different about these two. So 1 minute, and you can talk to a partner, but you're going to have to come back to me at 1 minute, and I'm not there, so it's going to be a little bit harder. But 1 minute, try and figure out what's different about these two. Okay, so start to wrap up those conversations. Okay, so I'm going to keep moving. There are probably plenty of differences here, but really what I'm looking at that's a big glaring difference is that this equation here has all these 1's and 2's in it. And what that means is that in this equation we had like a situation 1, which could be a container that maybe it has a piston that moves up and down and it's got a gas in there. Those are its little gas particles. And then something changes about this system. Still the same container, except for maybe the piston moves down, which changes the volume. And so the idea that we talked about there was if you knew all of these starting conditions and you knew the pressure, the temperature, but not the volume, well, you could calculate it using this equation. And so this equation was always when there was a change. There was some sort of change to the system. Well, now we're not dealing with that anymore. Now we're talking about this equation where the pressure, the volume, there's only one of each of those, and the number of moles and the temperature, there's only one of those. And this R, we actually haven't seen that yet, and we'll talk about that in just a minute. But this equation is used for, well, what if I don't want to talk about a change? What if I want to talk about a balloon? Just one balloon, no change, but I know the pressure, I know the volume, I know the number of moles, I know the R, which we'll get to. Can I find out the T? And the answer is yes. If you know 4 of these variables, then you can find the 5th. And so what you're going to write here for this question, the question that is, when would you use the ideal gas law? When you are looking at a single, so just one, a single gas system. System is just kind of the word for a thing, basically, a set of gas. And so when we're looking at a single system, we're going to use PV equals nRT. And so now let's start talking about that R. So I've got a piece of your STAR reference sheet, copy and paste it here, and what I want you to do is find the R value in this constants and conversion sheet. You have an R and a blank spot on your paper, so go find it right now, write down the number and all of its units, and I'll give you 30 seconds to do that. Okay, so hopefully you've found it. It's right here. And the reason why I was saying it was important to write down the units is because that helps us answer our next question. So this number, 0.0821 liters ATM over moles Kelvin. Usually when you do math, if you have these units and we try to multiply or divide things, actually the math doesn't work out unless we have consistent units. So the last question of our notes, what kind of units do we use? Well, they are right here. Pressure, volume, and T. So the pressure, ATM, we have it right there. The volume, well, if you look up here, liters is volume. N has to be moles because it's the number of moles, and then temperature, just like before, is Kelvin. So now that we have all this information, we have our equation. We know what units this information is. We're ready to go to a problem. So I'm going to stop this video here, and we're going to go to the next one, and you're going to flip your paper over.